Welcome. In this video, I'll introduce GenPRVE, a free tool for generating periodic representative volume elements in Abaqus. The tool automates random sphere packing, geometry creation, meshing, and the application of periodic boundary conditions. Creating periodic RVEs in Abaqus can be a real challenge. Manual sphere packing is slow and limited. Generating periodic geometry usually requires heavy partitioning. Meshing with periodicity is often error-prone, and applying periodic boundary conditions can be tedious and repetitive. GenPRVE solves all these challenges by automating the entire RVE generation process. GenPRVE comes with a number of features. It supports random sphere packing with volume fractions up to 50%. It can automatically generate periodic geometry with flexible inclusion types such as hollow spheres, solid spheres, or just voids. It produces a conforming periodic mesh and allows one-click application of periodic boundary conditions, both for elastic modulus and for shear modulus. All of these steps are fully automated, with no manual partitioning or scripting required. The workflow of GenPRVE is based on 4 consecutive steps. Each step builds on the previous one and must be followed in order. The process cannot be reversed because the output of one stage becomes the input for the next. Let's go through each step in detail, starting with Step 1. Step 1 is sphere packing. The method is based on molecular dynamics and Monte Carlo simulations. GenPRVE supports packing up to 50% volume fraction. For proper meshing, the minimum spacing between spheres is set to 2 times the mesh size. In terms of performance, small RVE with up to 100 spheres take less than a minute to generate. But large systems, such as 1,000 spheres at 50% volume fraction, may take several hours. In this step, we first define the mean radius and variance of the spheres, using a uniform distribution. For equal-sized spheres, simply set the variance to 0. Next, we specify the target volume fraction, which can be chosen between 0.1 and 0.5. Then, we set the RVE dimensions, Lx, Ly, and Lz. Once the inputs are ready, select Random Sphere Packing from the RVE Generation drop-down and press Apply to generate the packing. You can now see the random sphere packing generated in the message area below. The achieved statistics of the spheres are displayed here. Generating more spheres will generally give results that are closer to the chosen input values. If you're not satisfied with the current packing, you can simply press Apply again until you're happy with the outcome. The next step is to generate the geometry. After completing the sphere packing, define the geometry parameters. Select the inclusion type, which can be hollow spheres, solid spheres, or voids. Then set the mesh size percentage, which controls the geometry discretization. Next, from the RVE generation dropdown, choose Create RVE Geometry and press Apply. If you don't want to proceed with a periodic mesh and periodic boundary conditions, you can stop here and apply ordinary kinematic uniform boundary conditions. Else, continue to the next step. Once the geometry is created, the parts are automatically added to the assembly. Default materials and sections are also generated and assigned, but you can modify them later according to your study. To verify the volume fraction, open the part called Matrix Cut 00. Go to Query, then Mass Properties, and check that the matrix fraction corresponds to 1 minus the volume fraction you specified, as you can see here. If the values don't match, it's recommended to start a new model and repeat the process from Step 1. Step 3 is to create the periodic mesh. At this stage, You cannot change any parameters. Doing so will likely cause an error. From the drop-down, choose Create Periodic Mesh and press Apply. Partitioning for periodic meshing is now in progress. The duration depends on the size of the model, such as the number of inclusions and the mesh density. In this example, the process took about 7 minutes. Once complete, a periodic mesh is generated for both the matrix and the inclusions. The instances within the assembly are updated, and you can now inspect the model. If the completion message does not appear, it means the program encountered an error, and you will need to start over from step 1. Unfortunately, the more complex the model, the higher the chance of errors. But in most cases, this step will succeed, and once it does, you now have a periodic mesh ready for the next and final step. Step 4 is to apply the periodic boundary conditions. You can choose Step 4a to apply PBCs for the elastic modulus, which will compute E11, E22, and E33. Or you can choose Step 4b to apply PBCs for the shear modulus, which will compute G12, G13, and G23. You can alternate between them at any time. This step will check for any existing constraints or reference points and delete them before creating new ones. The tool automatically generates all required reference points, node sets, and constraint equations, so you don't have to do this manually. It creates periodic node-to-node constraints for both the matrix and the inclusions, whether the inclusions are solid spheres or shell spheres. Again, make sure you see the completion message in the message area. At this point, GenP RVE has finished its job. The periodic RVE is ready, and the remaining tasks depend on your specific study. These include adjusting the default material properties and section assignments, defining the matrix inclusion interaction, and creating analysis steps with the appropriate loading conditions. In the next part of this video, we'll look at an example of how the model is completed, from the GenP RVE handover through to the job results. Let's start with materials and sections. In the assembly, you'll see the instances that GenP RVE has generated. Default materials and section definitions are already assigned, and you can modify them to match the requirements of your study. Now let's create a step. In this example, we'll use an explicit dynamic analysis. Don't forget to turn on NLGeom. If you're working with a static step, NLGeom is also important, along with specifying a damping factor. Next, create an amplitude. Next, let's define the interaction between the matrix and the inclusions. We'll begin by creating two sets to represent the interaction regions. While in the assembly module, start with the inclusions. Hide matrix cut 01, so only the inclusions are visible. Then, from Tool Surface Manager, create a new surface and name it Surf I. Select them all, then choose brown for the outer surface. This is the region in contact with the matrix. Now, for the matrix, hide the inclusions and view only Matrix Cut 01. Selecting the interaction region here can be a little tricky, but I'll show you an easy way. First, let's create another surface and name it Surf M. Then, select everything. Switch to Biangle and set a small value, such as 4 or 3. While holding Control, deselect the 6 surfaces one by one, as shown. Now you've selected only the region that will be in contact with the inclusion. Press Done. Now let's define the interaction properties. Double-click to create a new interaction property and name it Dummy. I'll explain its purpose later. For this one, choose the typical normal behavior option. Next, create another property and call it CZM for Cohesive Zone Model. Add normal behavior and cohesive behavior. Then specify the stiffness coefficient as shown. Then add damage by defining the damage evolution and stabilization parameters as seen. Now, double-click on Interaction and select General Contact. Here, choose the dummy interaction property that we created earlier. Next, edit the individual property assignment. Select Surf I first, then Surf M, and assign the CZM property by moving them all to the right. It's important that the inclusion surface is the first pick and the matrix surface is the second. Otherwise, the analysis may not converge. We do this step to trick Abaqus into accepting cohesive properties for surface-to-surface contact. Finally, press OK to confirm. Now, let's edit our field history output as follows. And then define the boundary condition as a displacement. Before continuing with this example, let's take a look at this table. This table summarizes the boundary condition settings for each case. The columns represent the reference points, reference point 4, reference point 5, and reference point 6. And the second row shows the degree of freedom directions, 11, 22, and 33. The rows on the left list the modulus you want to compute. For example, to compute a normal modulus like E22, you would apply U2 at reference point 5 and leave everything else unset. And for a shear modulus like G12, you would apply U1 and U2 at reference point 4, while leaving U3 at reference point 4 unset, and setting all degrees of freedom at reference point 5 and reference point 6 to 0. For this example, we want to compute E11, so we will apply displacement U1 on reference point 4 and leave all other degrees of freedom unset. Finally, let's create our job and submit it for analysis. Please note that this job may take some time to run, since we are using explicit dynamics with many constraints and cohesive interactions. While this job is running, let's go back and set up the case for G12. Open Gen PRVE again and make sure the parameters are the same, especially the RVE dimensions and the inclusion type. Then choose Step 4B and press Apply. Once that's finished, let's set the loads for G12 as follows. Create another job and submit it. Now, let's look at the results. For the E11 case, the displacement was applied along the x-axis. You can see that the deformation pattern is uniform in that direction, which is consistent with an elastic modulus test. The output database allows us to extract the reaction forces and compute the effective modulus E11 from the applied strain. Next, for the G12 case, the combined displacements U1 and U2 were applied at reference point 4. The result is a uniform shear deformation in the xy plane. Again, the reaction forces from the boundary conditions can be used to calculate the shear modulus G12. Before we wrap up, a few notes. GenPRVE is a completely free tool, full and unrestricted, and it will always remain that way. Since it's an individual project, you may occasionally encounter errors. If you'd like the tool and its supporting documents, please email the address listed in the video description and request the GenPRVE package. Feel free to contact me with any questions, or if you need a specific capability that GenPRVE does not currently provide. If you find this tool helpful for your research, please cite the paper associated with this work. The details are in the description. The paper also provides in-depth explanations of the algorithms used to develop this tool. Thanks for watching, and until we meet again.